It's a black screen, as you can see right now. I don't know. It's again installing. Now, okay. It's this Windows 10 new version. They're pushing me to upload the Windows 10 or the Windows latest version. That is blocking my screen. Last thing I want is the update. I know it very well. Anyways, we had strategies. The three strategies, the three important strategies that we had was first a deadlock prevention, deadlock detection with recovery, and deadlock avoidance. And of course, we had a funny one that was Ostrich Algorithm. But now, the first thing that we need to study, in the meantime, we can talk about, is deadlock Ostrich Algorithm in deadlock. That's the first one that you will see. What the Ostrich Algorithm literally means is Ostrich Algorithm is basically no algorithm at all. It is a funny sounding algorithm, but it is one of the most popular algorithms still when it comes to the strategies for dealing with deadlock situations. Because the most important thing right here is the unpredictability. And although we talk about logical avoidance, we talk about how to avoid deadlocks best as we can, but still, we can never do that. We can logically never do it. So the only way that we can try to get out of this is by using some kind of strategy that will help us to ignore it. And yes, that's exactly what we do. We try to ignore the problem, pretending that if we ignore the problem, then the problem will sort of disappear. And that is exactly what we do. So we have this ostrich algorithm, as I say, but we call it ostrich because it's a funny bird, and ostrich is a funny bird that kind of like pretends that there is no problem. So when it sees a problem, it simply chooses to ignore. And that's what most of the engineers will like to do because remember, it's a project, it's a software with a commercial value attached to it. So you can't just keep going for an indefinite period of time, wasting your time and money thinking about or trying to resolve a hypothetical problem, a problem that is imaginary. Because how do they know that where, how do they know that where exactly the problem will be coming from? So there is no way to predict that who is going to use which, who is going to use which combination of software on their on their computer. So since we don't know and we can't make any imagination of that, so what will happen is they will have to deal with something else. In other words, they simply choose to ignore it. So when the problem comes, we will sort it out. But however, there are a bunch of people who will not accept that kind of excuse, that these are the mathematicians. So they say that it is totally unacceptable. Any problem must be solved. So the question that we sometimes ask from this ostrich algorithm is whose view, who chooses to ignore it and who chooses not to ignore it. Of course, the mathematicians, they are solution freaks and they will always try to solve any problem at any cost. Their view is to somehow deal with these problems, however imaginary and hypothetical these problems could be. Whereas on the other hand, the people, the engineers and the developers, they are not willing to pay a huge price for this sort of thing. Okay. So that there we are. We have two different viewpoints. I think we can enter now. Let me share the screen. Wait a minute. It always happens in the morning class, and especially on Monday morning class. The computer is shut down for 48 hours almost. Let me. What happened? Don't tell me again. The tab will hang. Everything hangs. Oh, Viber notification and everything. Give me a minute to try to solve it. Wait a minute, let me see. The computer's behavior is not very friendly. See? All right. So there we are. We are looking at deadlock recovery. That's the very beginning of it. We go to the strategies. Modeling was the important one that we talked about. The slides don't. Strategies. There we are. So as you can see, the three core strategies are there. The first one, obviously the one that I was talking about, Ostrich Algorithm. And if you move on to the next part, then you will see the first one is all about just ignore the problem. Okay. And this ignoring the problem is one of the key things that we will do. Wait a minute, it seems they're hanging again. Not responding. Close the whole. Oh, goodness me. The whole browser is closed again. Oof. Oh, what? Anyway, I mean, we continue without this one. Don't know when it will sort out. It's all white. Browser crashed. The point that we are talking about, so leaving behind that strategy that basically says that all you have to do is to leave the problem behind. I mean, move on, and whatever the problem is, the problem will stay there. When the problem comes, then we will solve it. Basically, because trying to solve an hypothetical problem doesn't really add any value to the project. So that is most of the engineers, that's what most of the engineers will be thinking about. Okay. The one that is important, however, is the first one that we'll be talking next. There are three things. One is the detection and recovery, one is avoidance, and one is, of course, prevention. These are the three things that we are going to talk about. So the first thing is prevention. First thing is deadlock detection and recovery. When it comes to detection, as the name suggests, that we will have to detect something, whether it has happened or not. And for that, we need a tool that is the resource graph that we talked about in the last class. In the tool, we will create a deadlock model. So once we create a model to see the deadlock has happened, then we can take some proper steps to overcome that particular problem or to get out of that problem. But once we know that that problem has actually happened. So that is our strategy. That is the strategy that we usually adopt. Okay, that's the strategy that we usually adopt. Can anyone suggest what to do with this one? File, but now you see it doesn't even give me. Okay, remind me later. Thank you very much. Warning, this irritating things. Okay, we quickly look at the ostrich algorithm that I was talking about. In fact, as I said, there's sometimes the only question they ask on this part is whose view is what? That is the question they usually ask. Just choose to ignore it. But then comes the detection with one resource of each type, which is pretty easy to understand and rarely comes, but now comes the most important part. Deadlock detection with with multiple resources of each type. Rather than going through the schemes that were in a textual way, this is the most important slide that we will be dealing with. Now here you go, and we need your engagement in it as well, okay? Because we want you to get engaged. This is the algorithm, and if you can answer these questions properly, then rest assured you don't have to worry about any algorithm-related problem in Deadlock Chapter, because we have one algorithm called Banker's algorithm. Still, behavior is not good. Okay, So to start with, the one that you are looking at is what we already know at resource graph. This is the resource graph. And in this case, on this page, we are trying to detect, remember, deadlock detection. As we say, deadlock detection. We are trying to detect a deadlock. So let's first get introduced to what is what. What is E? What is A? What is C? And what is R? Because these are the these four letters you'll have to remember. Not necessarily always they will give you the full word. E stands for existing, as you can see, the existing resource vector. E and A are two vectors, while C and R are matrix, that means table. This is one of the most important things. Okay, so we have E that stands for existing, and A that stands for available, and then we have C, which literally means the current allocation matrix that is at this very moment. Current literally means I can see that after the last allocation. After the last allocation, that means this is the current situation, allocation is right here. And request means that still how many other resources are being requested. So how many other resources are being requested? So that literally means that we still need some more resources to work with. In other words, if you consider P1, this is P1, this is P2, and this is process 3. So literally we say that at the very moment, for example, P1 is holding on one scanner, but also asking for 2 more tape drivers and 1 CDL. So the point here is, remember what we said earlier in our diners problem, that one of the diners is holding on a chopstick and waiting for the missing chopstick. And that created a condition that we called hold and wait condition, which basically was the beginning of the problem. So a question that I asked you, I remember at that point, is what is the most normal and natural way that we can expect that this guy will release the one chopstick that he is currently holding on? What do you think? The answer is, since he is asking for one more chopstick, give him one more chopstick. If you are the chopstick manager, like operating system is the resource manager, if you are the chopstick manager, then try to arrange one more chopstick. So where you will get it, it's up to you. But try to get it and give it to this guy, because he is holding on a chopstick not because that he loves to hold on chopstick, simply because he is feeling hungry and he wants to eat food. But with one chopstick, he can't eat food. So that's the only reason he is holding on the chopstick. Similar to that, in our, from the resource scenario, resource and process scenario, a process needs 3 resources to finish. Currently, he has only 1 and is requesting or waiting for 2 more. So unless you give him all the resources, he can't finish his job and he can't go back to sleep and free all the resources. So the question that we used to ask right there, if you can give him 1 more chopstick to this guy, you give 1 chopstick And what do you get back? You get back 2. Try to understand and uh, actually with this point. If this understanding is clear, then it will help you a lot in more complex calculation, fundamentally based on the same idea. If you give him one more chopstick, what do you get back? You get back 2. Not only the new chopstick, the one that you gave him, that will come back to you, but also the extra one that he was holding on. Because he will not be, after he finishes eating, he won't be needing any of these chopsticks. So he will just release both the chopsticks. Did we get it? So that is what is a fundamental idea in resource management. So let's come down to this one so we understand what this is all about. And also understand that this R is the fact that the request matrix, honestly, is the most unstable and unpredictable factor. And because I can tell you, because of this request matrix, the unstable and unpredictable request matrix, it is going to be, we need something called Ostrich algorithm. You get my point? It's so unpredictable, so unstable, that we don't know exactly what is coming. So although we will take some preventive measures and measures to avoid things logically, avoid deadlocks logically, but in the end, we can't guarantee that our operating system is strong enough to stop any kind of deadlock. No one can. No one. So that is where we still run the risk of getting involved in a deadlock. So now, let's start. The question that we are going to answer in this part is there a deadlock at this very moment? If I can write it down. Is there a deadlock? Now. Now means current. At this very moment. After the last allocation. So if you want to answer this, then naturally the way you can find it out, because that is what we call deadlock detection, remember? If you want to answer that, you have to find out one other thing. That is, can all the processes run to completion? Can all the processes run to completion at this stage? So first of all, is there a deadlock now? To find the answer, you have to look into another question. Can all the processes run to completion? It's the same thing. If they can run to completion, if the uh, if they run to completion, then it's most likely then they can the process run to completion, and if they run to completion, then obviously there won't be any deadlock. Okay. So that is the question that we are going to answer right now. So let's see what happens. So tell me, this is your turn. get engaged because I want you to get engaged in this algorithm. This is available after the current allocation. And then we have the request. So looking at the request of process 1, process 2, and process 3, tell me if you look at the available, oh, by the way, how did we calculate available vector? It's easy. Existing minus total current. You can see 4 minus 2. 2 is already allocated. So left is 2. 2 minus 1 is 1, and so on. Now, looking at these available matrix at this very moment, do you think any of these processes can be served if nothing changes? Can I serve P1? No, because P1 is asking for one CD-ROM, and we don't have that CD-ROM. Okay? So we can't. Remember, you have to give, well, you can say, you can argue that, well, why don't we give him 2 tape drivers? That's good. You can give 2 tape drivers, but you don't get back anything. And then you are stuck. That is the mistake that you will make. That will be an incorrect or careless resource allocation, because of which you will run into deadlock. Because once you give 2 tape drivers to process 1, and then you'll be left with 1 plotter, and you don't get back anything. Okay? So basically, we are actually on this page, we are doing not only detection. Detection is the final answer that we will, final question that we'll answer. Whether all processes can run to completion or not. But the way we approach it is what we will be calling banker's algorithm with multiple resources, one of the most and the hottest questions that we ask in the exam. Later on, we will use the banker's algorithm, the same thing. Just here we call deadlock, over there we call the condition of the system is safe, because we are trying to predict, we're trying to keep it safe. Anyway, so I reckon the only one that can run to completion is P3, right? P3 is asking for 2 tape drivers and 1 plotters. All of them I still have, so I can give them to P3 and P3 and run to completion. And when it is done, it will return everything, this extra one and the old one, back to me. So when it returns everything to me, what will be the available vector? Can anyone tell me? Do your calculation and send me a message. You have to. That is what you are supposed to do. What will be the available vector when P3 runs to completion? Anyone would like to volunteer? Give me the numbers. Anyone can tell me where exactly what should we write there? I can give you the answers, but if you don't understand this part, then there will be problems. You'll have problems later on. That's why I'm asking you. Sorry. If P3 runs to completion, so I write down the numbers, you do your brainstorming to understand. All right? According to my calculation, 2220. Is it right or wrong? If it is right, then try to figure out why I wrote that. Because you will have to do it in the exam. Stay prepared for that. With P3 running, P3 done, now we are left with P1 and P2, and we have 2220. Forget about this available. It's already been updated. Okay. Can we serve any of them? Yes, we can serve P2. So P2 runs to completion, and what we get back? 4, 2, 2, 1. Can I now serve P3? Sorry, P1? Yes, because we have recovered one CD-ROM, which we previously didn't have. Now P1 runs to completion, and after P1 runs to completion, we get with 4, 2, 3, 1. So literally that means in this context, we answer, is there a deadlock? Answer is no. Because all the processes after the current allocation can run to completion. No process deadlock. Okay? But suddenly, as I said, the most unpredictable part here is the request matrix. Suddenly, the request matrix changes. So how about now? Now that you have 2101 for P2, with 2220 left, can I now serve any of them, P2 or P1? No, because both of them were asking for one CD-ROM, which I don't have. I mean, forget about these two. Forget about these two. With 2220, can any of them be served to run to completion? No. So there will be a deadlock. Deadlock between process 1 and process 2. Because we don't have the available resources. The calculation that I want you to take part in is the same thing that we'll be doing later in a much more complicated way. The same thing. And we'll call it Banker's algorithm. Okay? Stay prepared with that. Hey, by the way, I have already opened quiz 2 and review quiz. So when you do the quiz 2, also do the review quiz, because it will be graded as well. So quiz 2 and review quiz, and also quiz 1, because some of you missed quiz 1, if anyone missed quiz 1. So all quizzes are now open until the end of this week. Okay? Until the end of this week. So make sure that you don't miss it this time. And the password for all the quizzes is 12345. You don't have to worry about that. 12345 is the password of all quizzes. Whenever you want, you just take it. All right. So since we understand what is deadlock detection with multiple resources, let's see about the recoveries. This is another problem. At the moment, available is 0. Can any of these processes run to completion? Yes, because this one is not asking for anything. But if it runs to completion, it returns only 1, so I updated it right here. But that's it, because none of these is basically asking for the middle resource. So all of them will be deadlocked. 2, 3, 4, 5 will be deadlocked. How can we recover from this problem? The recovery from the deadlock, the first one that we see through preemption, is not a feasible one. It's impossible to implement, and we know the reason why. Because impossible to implement it's simply because that the preemption, the recovery through preemption is hypothetical. Why hypothetical? Because the recovery through preemption is impossible. You can't enforce preemption on a resource that is dominantly non-preemptive. If it is non-preemptive, you can't force itself to behave as a preemptive one. So it is the type of the resource. So we can't do anything with that. The only logical thing that we can do about is the recovery through rollback. What is recovery? As we saw just now, that we use the resource graph, and on that particular graph, we use check pointing. Okay, so that is what we do. When a deadlock is detected, a process is reset to an earlier checkpoint that didn't have the resource. So how do we use this piece of technology? It's like at every allocation, at every point, that means we allocate a resource and we write it down, that what we did. So this allocation is what we'll be calling a checkpoint. So at every stage, after every allocation, we write down all the details, or we take a snapshot of the request and the request pattern, and not only the request pattern, but also the other pattern, that acquisition pattern. That is what we do. Okay. That is the first thing that we do all the time. So once we do that, then at every checkpoint, we have to ask the question, is there a deadlock, yes or no? If the answer is no, then we move to the next checkpoint. Okay? We continue to allocate resources. We create new checkpoints. But at any point, if the answer is yes, there's a possibility of deadlock, then we have to roll back. That is called rollback. And as we roll back, we start a different trajectory of resource allocation. So once we have that one, once we have that checkpoint, uh, understand that there is a checkpoint, and the checkpoint, from one checkpoint it moves to the next checkpoint, and as we progress, we keep checking whether there's a deadlock or not through our deadlock model. If we see that there is no deadlock, then we can move ahead. If we see there's a deadlock, then we just continue to uh, roll back to an earlier checkpoint. Now, these things are noted down in written to a file so that it can be restarted later. To be most effective, new checkpoints shouldn't overwrite old ones, but should be written to a new file. So as the process execute, a whole sequence accumulates, and that is exactly what we want. We want to store the entire sequence because we just never know where we will meet the deadlock and how many steps we will have to roll back. So that is what we are going to do. The recovery, when deadlock is detected, a process is reset to an earlier checkpoint that didn't have the resource. Then the resource is assigned to one of the deadlock processes. if the started process tries to acquire the resource again, it will have to wait until resource becomes available. Recovery through killing processes. Kill one or more. So the last option is, although it sounds logical, but it is not exactly logical. So kill one or more processes in the cycle. It's the crudest but simplest way of doing it. The first approach, repeating until the cycle is broken. And the number two, kill the process in the cycle. Check the cycle. If so, go back to the first line. So in fact, the brute force is the one that we, the users, we choose to use. We, the users, we always choose to use because we a little bit impatient. We just want to get rid of it as quickly as possible. And that is what we do. We choose to kill a process. Usually, these are the users. But the second approach is also a killing cycle, but that is often done by the kernel or the operating system. If the kernel has to do it, it may do it in a more accurate way, in a more logical way. That's what it tries to do. Okay, so that is what it does. The process victim should be chosen only if it can turn from the beginning with no ill effects. You have to choose a victim in order to release the resource. So all you need to remember here is the names. These are the most important names. That the first approach, the second approach, who does this one, who does that one. So that gives us an overall review of the things that we have studied so far. The Ostrich algorithm, and just ignore the problem. And then detection. The detection basically means with one resource. One resource is not an important one. The most important one being this one. Deadlock detection with multiple resources. And of each type, using existing resource vectors, then available resource vectors, the current allocation matrix, and request matrix. The recovery through preemption takes the resource away from the process, and if another process uses it, and then give it back without the process noticing it is highly dependent on the nature of the resource. Recovery through rollback. Checkpoint is used to store the process state that is used to reset when the deadlock occurs. And recovery through killing process, it will simply break the cycle. So these are the things that we just now studied. Now we move on to the next part, which is avoidance and prevention. As I said, in avoidance, we'll still use the resource graph, but this time to predict. To predict, and once we successfully predict it, then we can stay safe. That is exactly what we are doing. For prediction, we'll be still using the same resource graph, and we'll be doing the same thing that we just now did in deadlock detection. So basically, we will try to see if there's a way that all these processes can run to completion. So we'll talk about resource trajectories, safe and unsafe states, the banker's algorithm for single, and the banker's algorithm for multiple. This is the most important one. And for that, we will step out of this. We already did it, in fact. We already did it in the last one. That's the same thing. So let's see. The system must be able to decide whether getting a resource is safe or not, and only make allocation when it is safe. Is there any algorithm that can always avoid deadlock by making the right choice all the time? Yes, the deadlock can be avoided, but only if certain information is available in advance. That is the question. Only if certain information is available in advance. As I said, that it's not always possible. Here, in these calculations, we'll make some assumptions that as if we know exactly how many resources a process needs to run to completion. But that is not going to be the case all the time. So in that case, we will be needing not only that one, but also the number of resources. So the number of resources requested, as I say, is presumed or is assumed to be known. But as I use the word assume, in reality, no one knows exactly. Suddenly, from somewhere, there will be a request. Okay, so this is where we need to be very, very careful. But only certain information is available. So safe and unsafe state. So that leaves us to either a safe state or an unsafe state. And that is what we are going to deal with. The safe and unsafe states. A state is said to be safe if there is some scheduling order in which every process can run to completion, even if all of them suddenly request the maximum number of resources immediately. A system is in a safe state only if there exists a safe sequence. So the system state is unsafe when the above condition doesn't exist. So what does it mean? But if you go back to the example that we tried to do interactively, of course, I ended up giving you the answers. So in deadlock modeling, that's exactly what we're looking at. We said that there won't be any deadlocks. There won't be any deadlocks simply because. So there won't be any deadlock simply because simply because all the processes can run to completion, or at least there is one sequence of resource allocation that can make all the pending resources, pending processes run to completion. So that is what it is. That is what it was. So we try to resolve this issue to that from that end. If there is some scheduling order in which every process can run to completion, even if all of them suddenly request their maximum number of resources immediately. The system state is unsafe when the above condition doesn't exist. Now take a look at this one. So we have the one resource and the second resource. So one is the has and the max. So we have this one coming up, and so think about it. What is has? Has means the current allocation matrix, and this is max. Well, max is not R. So be careful when they ask you these questions, they can use different terms. So you will have to calculate. So max the R, because we need C, we need R, we need A, which is basically this one is A, and we need E. E means this one is E, the 10 instances. This is an example of the banker's algorithm with one instance, one resource, multiple instances of one resource. So see, the available is 3. How is 3? Because 3 plus 2 plus 2 is 7. 7 minus 10. 10 minus 7, sorry, is 3. So we have 3. Now, how will you allocate these resources? Well, the only way we can allocate these resources is take this one and give it to someone. But whom to give? So in this case, we give 2. 2 is, can we give 2 to B? Yes, we can give 2 to B. So we are left with just 1. But never mind, because B has reached its max. So B will run to completion and will return 5. Now this 5 can be given to C, because that is exactly what it's looking for. So C will run to completion and you will get 0. But no, you get 7 back. So now that you have 7, out of these 7, you gave 6 right here. So you're left with 1. But don't worry, with 6 more, process A can run to completion and will return 9 more. So 10. So that is exactly what happens right here. And that is exactly how we could avoid deadlock. This is avoiding deadlock. But what we call it is a safe, because there is at least one sequence of resource allocation that can keep the system safe. How about unsafe? This is what we'll see as unsafe. Because you see, unsafe because we still start from the same point, but we kind of carelessly give 1 to this one, make it 4. And then we are left with 2, so we give 2 to B, and we get back 4. But once we get back 4, we can't serve anyone. Because this one is asking for 5, and this one is also asking for 5. So these two a kind of, not yet deadlock, but we call it unsafe. If a system is in safe state, there won't be any deadlocks. If a system is in unsafe state, there's a possibility of a deadlock. The avoidance of deadlocks ensure that the system will never enter an unsafe state. So that is exactly what precisely what we do. That is exactly what precisely we do. Okay. And that is what we are doing right here. So that is what we do. So we somehow avoided this one. Okay. So we have 3 processes and 1 resource with 10 instances. For your mom and anybody. So the point that if a system is in the safe state, there won't be any deadlocks. But if a system is in unsafe state, there's a possibility of a deadlock. There's a possibility of deadlock. To avoid the deadlock, ensure the system will never enter an unsafe state. And that is something that we'll have to remember. The basic facts. So what are the basic facts? The deadlock avoidance, the safe and unsafe state. If a system is in the safe state, there won't be any deadlocks. If a system is in safe state, is in unsafe state, there's a possibility of deadlock. Possibility of deadlock. To avoid the deadlocks, ensure that the system will never enter an unsafe state. That is the bottom line of these principles. Okay, the point is that we are having this condition, and this condition is one of the 4 conditions that where we have the deadlock and some of the basic facts that we are looking at, and we'll have to keep an eye on that, on these basic facts. Okay. And we are trying to make sure that we stay safe all the time as possible. Okay, as much as possible. Okay. So next thing that we will be looking at, but remember these conditions, because sometimes in a tricky question they ask you what are the conditions, like in a banker's algorithm. Okay. As you can see, it will be safe, but then unsafe. The first two are the safe, but then it can suddenly become an unsafe state. So the next thing that we will talking about, and remember, we didn't discuss what I usually do is doing some exercises, and these exercises will be important, but although I don't know whether you didn't participate in this one. Okay, so try to understand the logic behind these allocation with multiple resources, because that's the most common question you will be getting in the exam. And for that, we will talk about it. We will talk about it in the next class, in the beginning. I will give you some exercises. But also from the next class, you should stay prepared. I'm not saying that we are jumping into any kind of presentation at the moment, but stay prepared with that. So the conditions that we use is attacking. I think prevention is something that we can talk about in the next class. A little bit distracted today as well. So we will do it in the next class, and I will take your attendance, because otherwise we will forget to take the attendance. No, I want to take the attendance. All of you, I think, I will give you the attendance. I want to take the attendance. No, I want to take the attendance. 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 So in the next class, we will remind me, just we will talk about the prevention, which is basically a little bit of thing left. But after prevention, I want to do some exercises like this one with you. That's basically what we'll be doing. The ones that I showed you at the beginning. This one. This is with multiple instances, the multiple resources, the same thing. That same thing here in this on this slide, because we called it a deadlock detection. Over there, we'll be calling it deadlock avoidance. So try to understand this particular slide at the moment. The rest of the things are really easy to just memorize, but this is the one where you have to apply a little bit of brain. It involves a little bit of brain work. Okay? So if you do it, then in the next class, after we finish, of course, we will start prevention. We finish, then we will get back to some exercises. Those exercises will be pretty helpful, hopefully. Okay? So that's all. And I will just leave you here and we will catch up on Wednesday. Okay. So bye for now.